Okay, we're going to wrap up the the normal distribution today. First, let's define percentile because we used that last class. We just didn't write a definition. So percentile is the percent of observations that are less than or equal to a certain value. So remember, like 90th percentile is the same as what we sometimes call top 10%. Okay? Most of what we're going to talk about today focuses on the empirical rule. The empirical rule is actually kind of a shortcut. So what the empirical rule tells us is it tells us the probabilities if we land on an exact standard deviation value. Okay? So it tells us that 68% is within one standard deviation of the mean. 95% is within exactly 2 standard deviations of the mean. And 99.7% is within 3 standard deviations of the mean. Okay, so what we can do with that is we can look at a normal distribution. I'm going to sketch one right over here. And I'm actually just going to make the assumption that this is the standard normal distribution. So it's normal with a mean of 0 and a standard deviation of 1. So that puts 0, 1, 2, and 3. And then -1, -2, and -3. But this empirical rule applies to any normal distribution. So these could be any numbers for the mean and standard deviation. As long as it's normal, this empirical rule will apply. Okay, so with that, I know that between one standard deviation above and below the mean, that's going to include 68% of my data. Or in other words, each of these is 34%. Okay? When I go out to 2 standard deviations, I now have a total percentage of 95%. And since I've already accounted for 68%, that has a bad glare on it. Well, I wonder why that is. See if I can fix that. That's a little better. Oh, too dark. Okay. We'll go with that. That's going to have to work. Okay, so since I have a total of 95, but I've already accounted for 68, that leaves me 27% between these two sides. And if I divide that by 2, that leaves 13.5% for each of these individually. Okay, so at this point, I've got a total of 95%. And then when I go out to 3 standard deviations, that accounts for a total of 99.7%. I've already accounted for 95% here. So 99.7 minus 95 leaves me with 4.7%. And when I divide that into 2 pieces, I get 2.35% for each of these. Okay. And you'll notice we haven't quite gotten to 100% yet. We've gotten to 99.7. So that leaves me 0.3% for these tiny little areas outside of 3 standard deviations. And if I divide that by 2, that's 0.15%. That is a very, very small amount. So if you think about, I don't know, whatever measurement we're looking at, if someone falls more than 3 standard deviations, either above or below the mean, they are incredibly unusual because they're in the either top or bottom 0.15% of the whole population. Okay, so this is a super nifty little shortcut, but just a reminder, it really only applies if you are on exactly 1, 2, or 3 standard deviations from the mean. If you're not exactly on a standard deviation, you need to calculate the z-score and then do normal CDF. Okay, so we're going to look at a couple quick examples. Just a side note, you can cross off this methods for assessing normality. We'll get to that in January, but we're not going to have time for it now. Okay. I'm going to skip example A. It's super, super straightforward. I'll put it on Schoology for you. Okay, but I'm going to go look at part B. It says, we're assuming heights of college women are normally distributed. That's helpful. Mean of 65, standard deviation of 2.5 inches. So we would note that it's normal. 65 is the mean, and 2.5 is the standard deviation. So draw and label. You can make your curve as wide or as narrow as you like. I typically like to draw mine wider just because it allows me more space to label my graph. Okay, so 65 in the center for the mean, and each standard deviation is 2.5. So 67.5, 70, 72.5. And same thing on the other side. 62.5, 60, and 57.5. And I don't want to leave that graph without a label. These are heights measured in inches. Okay, and so what percent of women are taller than 65? Well, 65 is the mean, and we know for a normal distribution, the mean is in the center. Taller than would be to the right, so that's going to be 50%. What percent of women are shorter than 65 inches? Again, 65 in the middle, shorter than is to the left. That's also going to be 50%. Okay. 62.5 to 67.5. Well, the nice thing here, I could do a z-score here, a z-score here, and then do normal CDF. But since 62.5 and 67.5 are on exact standard deviation marks, which I didn't draw my graph very well, but suppose it was nice and symmetrical, they're exactly 1 standard deviation above and below the mean. The empirical rule tells me that 1 standard deviation on each side of the mean contains 68% of the data. Okay. What percent of women are between 60 and 70? Again, going out 2 standard deviations on each side, perfectly on that standard deviation mark allows me to use the empirical rule, which says 95% of the values should fall within 2 standard deviations. Okay. Now the next couple get a little bit more creative. So 60 to 67.5. Well, 60 is 2 standard deviations below the mean. 67.5 is only 1 standard deviation above the mean. So I have to remember that this middle section, 1 standard deviation on each side is 68%. And then if you remember on the front of our outline, we broke these sections up and we said, okay, well, this is 13.5%. So 68% plus 13.5% gives me a total of 81.5%. Again, I avoided having to do all of the work of z-score and normal CDF when I noticed that both of these were on exact standard deviation values. Okay, shorter than 70 inches. Here's 70 inches. Shorter would be everything below it. It's actually easier, in my opinion, to figure out what the percentage is above 70% and then just subtract that from 1. So this little section right here is from 2 standard deviations to 3 standard deviations. That's 2.35%. And the very farthest little section past 3 standard deviations is 0.15%. So 2.35 plus 0.15 is 2.5%. So if I know that above 70 is 2.5%, then shorter than 70 inches would be 97.5%. Now, of course, you could get that by adding up all the sections below 70. I just think that that was faster to add up what's above it. Okay, and then it says approximately how tall would a woman need to be in order to be located in the 50th percentile? So remember, percentile is less than or equal to. So I want to find where there's 50% less than or equal to this particular value. So 50th percentile is pretty straightforward because that's got to be right down the middle. Or in other words, it's got to be at our mean, which is 65 inches. And then 97th percentile, I need to figure out where I hit 97. So here I've hit 50%, right on the mean. At the next standard deviation mark, I've hit the 50% plus another 34, which would be 84%. So I'm not at that 97th percentile yet. This is 84th percentile. And then remember the next section is 13.5. So when I get to 70, I would be at 97.5%, which is the 97th percentile. So that would be 70 inches. Okay, hopefully that's making sense. Go ahead and try letter C. It shouldn't take you too long. And then when you're done with that one, I'm going to go do letter D with you. So pause the video if you need to. Okay, so letter D, I'm going to go fairly quickly through it. I don't think it combines a few ideas from this unit with last unit. So a vending machine automatically pours hot drinks into cups. The amount of hot drink dispensed into a cup is normally distributed with a mean of 7.6 ounces and a standard deviation of 0.4. Normal, mean of 7.6, standard deviation of 0.4. Draw and label. Okay. Here is my normal curve, mean of 7.6. Each standard deviation distance is 0.4, so that's 8, 8.4, 8.8, 7.2, 6.8, and 6.4. And I'm going to label that as ounces. Okay, so estimate the probability that the machine will overflow an 8-ounce cup. Overflowing would mean that we went over the allotted 8 ounces that are supposed to be in the cup. So that would be the probability that X is greater than 8. So we have two options here. I could not even look at the graph really, and I could go, okay, I'm going to calculate a z-score for 8. I'm going to do normal CDF, and then that'll give me my answer. And that would be great. But if I happened to glance at the graph, I might go, oh, 8 falls on an exact standard deviation value. And so I can use the empirical rule to figure out the probability that we will go over 8 ounces. So I'm going to remember that, of course, the middle is 50%, and the next section is 34 on either side. Okay, so I know that I have 50% and 34, which is 84%. So above 8 ounces would be the opposite of that, which is 16%. I'm going to write that as 0.16 because it asks for probability. Typically, that is answered as a decimal. Okay. The next one says that it will not overflow an 8-ounce cup. That would be that our ounces are less than or equal to 8, which will be the opposite of overflowing. So that would be 0.84. All right. Number 4, the machine has just been loaded with 850 cups. That's going to be important in a second. How many of these do you expect will overflow when served? So a set number of trials indicates that number 4 is binomial with an N of 850. And we are looking for overflowing as our success. So our probability we just found using the empirical rule of overflowing is 0.16. Our X would be number of cups that overflow. And we were asked to find how many we expect, which is the mean. For binomial, which is N times P, that formula is on the formula chart. That is 850 times 0.16. And I get 136. That's a mean, so it needs units. So that's 136 cups. Okay, number 5 says estimate the probability that the machine will not overflow an 8-ounce cup until the 4th cup. That until tells me that this is geometric. It's going to not overflow until the 4th, so we're still considering overflowing the success. It's not overflowing until the 4th means the 4th one does overflow. So probability for overflow is 0.16. X would be number of cups until first overflow. And we want the first overflow to be the 4th cup that gets filled, which means that the first 3 don't overflow. Oh, that's a 3. 0.84 to the 3rd. And then the 4th one is an overflow, 0.16. 0.84 to the 3rd times 0.16 gives us a probability of 0.095. So hopefully you're seeing that we can use a normal distribution to get a probability that then we could use in a geometric distribution or a binomial distribution. Part 6, estimate the probability that if 10 cups are randomly selected, exactly 8 will not overflow. This 10 cups tells me that it's binomial. Our N is 10. We're looking for 8 that will not overflow, so our probability of success is not overflowing, which is 0.84. X is number of cups that do not overflow. And we want that to be 8. So this would be 10 choose 8, 0.84 to the 8th, 0.16 squared. I'm going to use binomial PDF with 10, 0.84, and 8, which gives me a probability of 0.286. Okay. I am also going to go real quick and do that very last one at the end of the outline that we didn't quite get to in class, and then we'll call it a day. But I need to plug in my computer, so I'm going to pause this for a sec. Okay, all good. Let's go do that last one. Okay, so on this last one, we were looking at, let's see, nitrogen dioxide concentration. And in part 1, we were told the, mean was 36.92, standard deviation was 11.32, and it's approximately normal. All of that noted here. We were looking for what percent of observations falls between 14.24 and 59.6. I didn't bother drawing and labeling every value on the curve. As you can see over here, I drew a very rough sketch. So I didn't even consider using the empirical rule here. I just went ahead and went straight for z-score for 14.24 and a z-score for 59.6. So I actually got symmetrical z-scores. That doesn't always happen, but it did on this one. So I wrote my probability out that x was between those two values. I converted that to a standardized probability statement. And then I just went to my calculator and did normal CDF with the lower z-score as my lower boundary and the upper z-score as my upper boundary. And that gave me this probability. Okay, so part 2 says inside what interval is it guaranteed? Now, actually, we'll just read it and then we'll talk about it. Is it guaranteed that at least 89% of the concentration observations will lie? This is not actually worded as well as it should be. Inside what interval, and this should say centered about the mean. Because what that implies is that this 89% that we're looking for is the middle 89%. Without that phrase, I don't know if I'm looking for the middle 89%, the left 89%, or the right 89%. So our goal is actually to figure out the two different x values that are the lower boundary and the upper boundary for the middle 89%. So remember, when we have a percent and we're working backwards to an x value, we're using the backwards normal distribution feature in our calculator, which is called inverse norm. And so when I go to inverse norm, so I'm going to go to second bars, which is the distribution menu. I'm going to choose inverse norm, which is the third one. And then I'm going to tell it the area that we know. We know an area of 89%, which I'm going to type in as 0.89. Remember, we leave our mean and our standard deviation as 0 and 1. And then that 89% is not the left, It's actually the middle 89%. So I'm going to paste that, and I'm going to remember to write it down. 0.89 center. And what that's going to give us is it's going to give us 2 z-scores. And interestingly enough, those 2 z-scores are the same value, but one positive and one negative, which if we think about it, that makes sense. If we're centered at the mean, then we should be matching on either side in terms of how many standard deviations above and below we are. Okay, so our z-scores are plus and minus 1.598. So 2 different z-scores, positive 1.598, negative 1.598. We need to solve them each separately. So I'm going to set up the z-score formula. X minus the mean of 36.92 divided by the standard deviation 11.32. And I'll come back and solve that one in a minute. My other one is going to be the other z-score. Negative 1.598 x minus 36.92 divided by 11.32. So 1.598 times 11.32 plus 36.92. This x value is 55.009. Negative 1.598 times 11.32 plus 36.92. The lower x value is 18.831. So that would tell me that the middle 89% of concentration observations, it's a mouthful, are between 18.831, and these values are measured in the units given up here, ppb, and 55.009 ppb. Okay, hope this helps. Let me know what you have questions on.